Okay, let's dive into this. We're looking at something pretty fundamental in data analysis today, right?
Exactly. That age-old problem.
Yeah.
You've got data, you think there are groups in it, but how many?
Yeah, guessing the number of clusters up front, which, lots of traditional methods make you do, feels so arbitrary sometimes.
It really can be. And getting it wrong means you might miss what the data is actually telling you.
So the material we're exploring today points to a different approach. Dirichlet process mixture models, DPMMs,
That's the one. They sort of flip the script because you don't need that initial guess about cluster numbers.
which sounds almost too good to be true. So how do they manage that? The sources mentioned it's probabilistic, non-parametric.
Right. It's about letting the model figure out the complexity, the number of groups, based on the evidence in the data itself. It's not fixed.
Okay, so what's under the hood? What are the core ideas driving this?
Well, it builds on some familiar statistical concepts first, like the beta distribution. Useful for probabilities between two things, like a proportion.
Okay, yeah, like flipping a coin, but it might be biased.
Exactly. And then you've got the Dirichlet distribution, which is like the beta, but for, multiple outcomes. Think proportions across several categories.
Got it, standard stuff. But the sources really emphasize the Dirichlet process part. DP, that notation.
Precisely. That's the key innovation. The Dirichlet process isn't just one distribution. It's a process that can actually generate distributions. And the crucial part, it can handle potentially infinite categories.
Infinite categories, that sounds abstract. How do we wrap our heads around that? Did the sources offer a way to picture it?
Yeah. Thankfully, one of the papers used a great analogy, the stick-breaking process.
Stick breaking. Okay, tell me more.
Imagine you have a stick representing all possible probability, like 100%. You use beta distributions to break off a piece. That piece's size is the probability for the first category, or cluster.
Okay.
Then you take the remaining stick and break off another piece using another beta draw. That's the probability for the second category.
Aha, so you keep breaking off pieces from what's left.
Exactly. And because you're always breaking off a fraction of what's left, mathematically, you never truly reach zero. There's always a tiny bit left, meaning there's always a possibility, even if small, of breaking off a new piece, creating a totally new category.
So that represents the potential for a new cluster to emerge at any point, capturing that infinite possibility.
You got it. It makes the idea much more concrete than just saying infinite possibilities.
Okay, that helps a lot. So how does this stick breaking translate into actually clustering the data points we have?
It works iteratively. You look at each data point, one by one, and for each point the model decides, should this join an existing cluster or should it start a new one?
And what guides that decision? Is it just random?
Not random, it's probabilistic, based on the structure from the Dirichlet process. Points are generally more likely to join clusters that already exist, and the bigger a cluster already is, the more attractive it becomes.
Ah, that sort of rich get richer idea. Popular clusters tend to attract more members.
Exactly that intuition. It prefers fitting data into existing patterns if possible.
But what about starting a new cluster if a point doesn't seem to fit well anywhere existing?
That's where the other part of the DP notation comes in, that alpha parameter, the concentration parameter.
Alpha? Right, what does that do?
Alpha controls the probability of breaking off a new piece of the stick versus assigning to an existing one. A higher alpha value makes the model more adventurous, you could say.
More adventurous?
Yeah, increases the prior probability of creating new clusters. So you might end up with more, possibly smaller clusters. It encourages diversity.
And a lower alpha.
A lower alpha makes it prefer the existing clusters more strongly. It's more conservative, leading to fewer, larger clusters generally. It sort of concentrates the probability mass into fewer pieces of the stick.
I see. So the model isn't stuck. It uses the data and this alpha parameter to dynamically decide if a new group is justified by the evidence. That's the non-parametric aspect.
Exactly. The number of parameters, which includes the number of clusters here, isn't fixed beforehand. It emerges from the data fitting process.
Which, as the sources suggest, lets DPMMs find structure that fixed cluster methods might totally overlook, like small, subtle subgroups.
Precisely. It adapts to whatever complexity is actually there.
So, wrapping this up, what's the big takeaway for someone listening? Why should they care about DPMMs?
It means you have a much more flexible, data-driven tool for clustering, especially when you genuinely don't know how many groups to expect. It avoids imposing potentially wrong assumptions.
You let the model tell you about the structure.
Right. You get insights that are grounded purely in the statistical evidence within your data.
And that core idea that a model can determine its own complexity just by observing the data, that's really something powerful to think about, isn't it?
It definitely is. It opens up a lot of possibilities for more nuanced understanding.